on question 4, and the information says the graphs of f of x is equal to x plus p all squared plus q and g of x is equal to a over x plus b plus c are drawn in the sketch below and have the following properties. So we have a 5 over 2 and 0 is a point on the graph of f. So that's just a point. And we can see that it's an x-intercept. P is the turning point of f and lies on the vertical asymptote of g. So here's P, the turning point line on this vertical asymptote. Then we have the horizontal asymptote passes through 0 and 2, so there it is. And then we have the vertical asymptote passes through 1 and 0, and so that's it. And the horizontal asymptote passes through 0 and 2. The graph G passes the origin. So we can see now that the graph of G also has a coordinate at the origin, which is of course 0 and 0. So the first question is, show that the equation of G can be written as this. So they basically just want us to find the equation of G. Okay, so now when finding the equation of G, there's just something that we need to remember. G is a hyperbola, and the general equation of a hyperbola is y is equal to a over x minus p plus q. Remember, P is your vertical asymptote and then Q is your horizontal asymptote. And you saw that they actually did give us these asymptotes, so we can go ahead and look for them. First of all, we know the vertical asymptote. It's this one over here. And so the equation of it, because it's a vertical line, it starts as x is equal to, and because it passes 1, x is equal to 1. And so we can see that our P value is going to be 1. And we have a horizontal asymptote, which the equation of y is equal to 2 because it passes 2 on the y-axis. And so we know our q is equal to 2. Okay, so since we know these two, we can go ahead and just substitute them into the equation so long. So we have y is equal to a over x minus our p is 1 and then plus our q is 2. Okay, so all we have to find now in this is just the value of a. And since a is the only thing missing, just to find a, we basically just have to substitute a point, because if we can fill in an x value and a y value over here, this will become an equation where we have to solve for a. So let's see what point they gave us on this graph of G. So looking at the graph of G, remember that they said that this graph passes through the origin. And remember, the origin is this point over here and its coordinates are 0 and 0. So that's another coordinate on the graph of G. There's no other coordinate they give you. So let's go ahead and substitute 0 and 0 into this equation. Of course, we'll be substituting this as x and that as y. So we're saying that 0 is equal to a over, then we have a 0 for x, minus 1 plus 2. So now we're going to have, we have the 0 is equal to, we have a over 0 minus 1. So 0 minus 1 is going to give you a negative 1. And a divided by negative 1 would be negative a. And then we have plus 2. And then just to make the a positive and solve for a, we can just take the a over. And so we have a is equal to 2. So there we go. We have everything here. We can go ahead and conclude that y is now equal to 2 over x minus 1 plus 2. And that is, of course, what they told us to find. Okay, moving on to 4.2. So 4.2 says that we have to calculate the coordinates of P. So finding the coordinates of P. Remember, what did they say about P? They said that P was the turning. It is the turning point of F, and it lies on the vertical asymptote of G. So let's see what we can get from this. If this is our turning point and it lies on this vertical line, then it means that this coordinate, since this is an x value, it has the same x value as this over here because it lies on the same vertical line. It's on that line. So the x value is 1 and then the y value, we don't know that. Okay, so let's go ahead and see what else we can find in order to find that P. The equation of the parabola, they gave us that. They gave us that f of x is equal to this, okay? But remember, the original equation of the parabola in turning point form actually looks like this. So that equation actually says that y is equal to a bracket x minus p all squared plus q. That's what that equation actually says. And so I'm going to use it in this form just so that I don't get confused by the way they put it. Okay, so another thing that we can do, so we know there's something that we know here. Remember that P and Q are the coordinates of your turning point. P is the x coordinate of your turning point, Q is the y coordinate. So we know something about the turning point. We know the x coordinate of the turning point. So we know that that x coordinate is P, and then the y coordinate, we don't know that yet. So we can go ahead and substitute that into our equation so far. So I'm going to put in P. So I just have so long that y is just equal to a bracket x minus, our P was 1, so it's minus 1 all squared plus q. Now, notice in this, we still don't have a. So let's look at the general form that they gave us for f of x. They said that, notice that they said f of x is equal to x plus p all squared plus q. There is nothing in here. There's no number in front here that they put. So it means that by default, there's actually a 1, an invisible 1. In front of every bracket that doesn't have a number in front of it, there's an invisible 1 there. So that means the value of a is 1. So we can go ahead and just put that in now. We know that a is now 1. So I'm going to erase that and just put 1. Okay, so now that it looks like this, we can see that the only thing we need to find is just the value of q. And clearly to find the value of q, you can see that q is the only thing missing now. If we had a point, see an x and a y coordinate, we'd be able to find the value of q. So let's look on the parabola and see if they gave us a point. And I remember they did. They gave us an x-intercept over here. They gave us 5/2 and 0. So we can substitute that into that equation in order to find q. So let's go ahead and do that. We're going to substitute 5/2 and 0. And of course, we're substituting this as this is our x value and that's our y value. Okay, so we're going to say that 0 is equal to, and then I'm not going to rewrite the 1 because 1 multiplied by anything really just stays the same. So I'm going to just start with the bracket. And so we have the 5/2, then minus 1 all squared plus q. Okay, so you can go ahead and just punch this all into the calculator since they're all numbers. And when I put that in the calculator, notice I get a 9/4. So if this whole thing becomes 9/4, it's like taking the 9/4 over because I just want to leave q on its own. So I'm leaving q on the right hand side, and that became positive 9/4. I'm taking it over, and so I'm going to get a negative 9/4. And there we go. So that means we have found q, and we also know what the p value was. So they wanted us to find the coordinates of p. So just make sure to conclude. We're saying that therefore p is the point 1 and negative 9/4. Okay, moving on to the next question. We have 4.3. They say write down the equation of the vertical asymptote of p if p of x is equal to g of x minus 1. So they're introducing a new graph here called p of x, but p of x is formed by saying g of x minus 1. So you have to remember what it means to subtract 1 from the x. So when you add or subtract directly from the x, this is a left or right movement. But now when we have a minus, so have minus 1, then this means that it's going to move to the right, specifically just by 1 unit. It's moving 1 unit to the right. So the thing about these questions, you first have to interpret what's going on. So after interpreting what's going on, let's go ahead and focus on what they want. They don't want the entire equation of g of x. They don't want you to do that to the entire equation. They specifically just want the vertical asymptote. So the vertical asymptote of g itself before, okay, was just, so we can go ahead and look at it. It was really just this over here. That's the vertical asymptote. And the equation is x is equal to 1. So if the original one was just x is equal to 1, and the new one is now saying we have to say x minus 1. We have to remove a 1 from there. And we are interpreting this as it is moving or shifting 1 unit to the right. This is what really happens. We're going to look at on our graph, we need to move this vertical asymptote 1 unit to the right. So it's at 1. If you move it 1 unit to the right, it will now be at 2. Okay, so now since it's at 2, the new equation is going to be x is equal to 2. So that's what happens over there. So let's go ahead and say x is now equal to 2. So you can also just show them your calculation. You can tell them that, you see, you interpreted that it's moving 1 unit to the right. And when you're looking at the Cartesian plane, 1 unit to the right means that you're adding 1. See, that's why you need to always differentiate between the way they put it as an equation and the way it actually moves on the graph. On the graph, 1 unit to the right is plus 1. But when they interpret it as an equation, they will say x minus 1, because minus means to the right, but plus means to the left as an equation, but not when it's actually moving on the graph like here, like when we move this 1 unit to the right. So of course, this equation is just x is equal to 2. That is the new equation of the vertical asymptote of p of x. Okay, so that is 4.3 done. And now we move on to 4.4. They say, determine the equation of the axis of symmetry of G in the form of y is equal to mx plus c if m is smaller than 0. Okay, so they want the equation of the axis of symmetry. This is work that you would have had to study already. You need to know about your axis of symmetry, the points of intersection of a hyperbola. So let's go ahead and look at the graph of G, that hyperbola. So when we're looking at this graph of G, let me just get rid of some of these. This graph of G will have 2 axes of symmetry. It will have one that looks like this. So this one, notice that this axis of symmetry, and let me actually just move it down a bit to make it pass like that. Okay, so it will have this axis of symmetry, and this one is the axis of symmetry with a positive gradient. Okay, and you can see that because the graph is increasing. Remember, you always look at graphs from left to right, like you read, because that's how the numbers increase, okay, on the x-axis. So this is the one that is increasing. And let's just remember, because if you remember the way the equation of this axis of symmetry is, the other one will not be difficult to remember. So this one says y is equal to, and here's where it actually becomes really easy. Remember, the general form of this, of the hyperbola, is y is equal to a over x minus p plus q. So the axis of symmetry, the equation is y is equal to x minus p plus q. That's the one with the positive gradient. Okay, so you see why I say it's actually easy to remember if you remember the general form of this. Then the one with the negative gradient that looks like that one that is decreasing because this line is going down, that equation, so this one has a gradient smaller than 0. The equation of this one is y is equal to, and what we do is we put a minus in front of the x minus p, only in front of those two. So minus, so we open in a bracket x minus p, then we have plus q. Then you can go ahead and multiply that minus in. So it means that the equation is y is equal to negative x plus p plus q. So that's the equation you need to be working with, the one with the negative gradient. So if we put in that down, we have y is equal to negative x plus p plus q. So now that we have this equation, let's go ahead and remember what p and q was. Remember the vertical and the horizontal asymptote of the hyperbola. So in the hyperbola, remember the vertical asymptote was the 1, and then the q was the horizontal asymptote. So p was 1 and q was 2. So we're just going to fill that in here. So we're saying y is equal to negative x plus 1, and then q, of course, was the 2, so plus 2, it's positive. So y is equal to negative x plus 3. That's the equation of your axis of symmetry with a negative gradient. Okay, and now we are at 4.5. We are told to write down the equation of k if k is the reflection of G about the x-axis. So remember, with reflections, you just have to think about which axis is it being reflected in and what will change as a result of that. So a simple diagram of this, if we had a Cartesian plane and I just drew, let's say, an exponential function, for example, like that. If this graph, let's call it f, if it was reflected about the x-axis, so here's your x-axis, it's going to look like this. Now notice what changed. The x values are still exactly the same. You see this, it still has this x value as this one's x value as well. The only thing that changed was the y values. So these ones, like this point, has a y value here. But this one that is right under it has a negative y value. So it means that when you reflect something about the x-axis, it causes the y values to change. And really what you just do to the y values is that you take them and you multiply them by -1. So this will happen to all the y values on this graph. Okay, so in the case of G, this is what happens. So also just notice that they're not really asking you for a point, they're asking you for the equation. So write down the equation of K. K is a new equation and it's a reflection of G about the x-axis. So this is how we can write it. K of x is our new equation and it is formed by taking G and reflecting it in the x-axis. Remember, when you reflect it in the x-axis, it causes the y values to change. In other words, you take the y values of G and you multiply it by -1. So it's like I'm saying y values of G times -1. Now, instead of saying y, I'm going to use G of x because G of x really just means y. So I'm saying that is G of x being multiplied by -1. Or you could just write it as negative G of x. So that's the new equation of K of x. So let's apply this into this. Remember, G of x is equal to an equation. So we're going to take that equation that G of x is equal to. We already got the equation in the first question. This is the equation of G of x. This is our G of x is equal to this whole thing. So we're going to just go ahead and substitute this in place of G of x. So saying that K of x is equal to, we have the negative, and then we're going to just open a bracket for G of x. So we have now 2 over x minus 1 plus 2. Okay. So now that we have this, let's go ahead and just multiply this negative into the bracket. So K of x is equal to taking this negative and timesing it into this bracket. Remember that negative is like a -1 and it's multiplying by 2 over x minus 1. So we're just multiplying those numerators. So we have -2 over x minus 1. And then this negative again is going to multiply to the 2 and give you a -2. So that is your new equation of K of x. Okay, so that's 4.5 done, and we are moving on to 4.6. So 4.6 says, for which values of x will f prime of x multiplied by g of x be greater than 0? Okay, so first of all, let's talk about what they mean by f prime of x. F prime of x is the derivative of f. Remember that f is this parabola. If we derive this parabola, let's look at what it's going to become. You first have to just look at the way f looks. It's concave up. So if you have a concave up parabola, when you derive it, it will become a line, but it will be a line with a positive gradient. So it's going to be a line that looks like that. Okay, so this is just something you need to also just remember about functions. So if you derive a concave up parabola, it's going to just become a straight line with a positive gradient. If it was a concave down parabola, it will become a straight line with a negative gradient. And really the reason why is because the parabola is in the form of y is equal to ax squared plus bx plus c. If it's concave up, it means that a is positive. And if a is positive, when we're deriving this, what happens is that you're going to have the a times the 2. The 2 is already positive. So this 2a is still all positive. Then we have x plus b. So you can see 2a is going to be positive. And since this is a straight line, it's in the form of y is equal to mx plus c. 2a would be your gradient. That's why the gradient will always be positive in a concave up parabola. Okay, so we know what that graph is going to look like, which we will draw. But then let's also just understand what exactly are we multiplying together. So when they're saying f prime of x, they're really just speaking about the y values of that graph, of that straight line that this is going to be. So it's the y values of that graph. And g of x would be the y values of g as well. And that needs to be greater than 0. So let's think about the type of numbers that will help us get values greater than 0. So if I take a positive number and I multiply it by a positive number, then I'm going to get a number greater than 0. Also, if I take a negative number and multiply it by a negative number, I'm going to get a value greater than 0. So this is what we need to look for. When we're looking at these, we're going to look for places where f prime of x, the y values of f prime of x, is positive, and for the same x values, the y values of g of x must also be positive. And then, of course, we will also look for the places where the y values of this graph is negative, and at the same time, the y values of this graph is also negative. That's what we're going to look for. Okay, so remember with this question, we're just looking for places where f prime of x is positive, but at the same time, g of x is also positive, and these refer to y values. Okay, so with this now, let's go ahead and first sketch f prime of x, because we don't have that. We only have f of x, which is the parabola. So when we're sketching f prime of x, just remember it's going to be a straight line with a positive gradient. But it is something else we also know about this straight line. You see the turning point over here. Looking at the x value of the turning point, you only focus on the x value. The x value of the turning point was 1. It means that that straight line is going to have an x-intercept at 1 as well. Okay, so this is how it always works. When you have a cubic function, you find out that the point of inflection is going to be the exact same x value as the parabola, the derivative of this cubic function's parabola, right? This parabola is going to also have the same x value in its turning point. And then if you derive this parabola, it's going to form a straight line graph, right? That has a positive gradient, but that straight line is going to have an x-intercept with the same x value as that turning point and as the point of inflection in the cubic function. So we know now it's going to have an x-intercept at 1. So we can go ahead and mark that. It's going to have that, and it's just going to be a straight line that basically just goes like that. Okay, so we're only going to be focusing on g and f prime. So let me highlight them in these colors. Okay, now that we have the graphs both written down, all we're going to look for is the y values of these graphs. So first of all, we're looking for where are the y values both positive. So since the y values must both be positive, we can focus on only this part of the y-axis. It just means we're only going to focus on these two quadrants, the first and the second quadrant. So you can ignore this for now. We're only going to focus on that. So we're going to look for places where these two graphs exist together. So over here already in the second quadrant, you can see we already only have g of x. So f prime of x, that graph, is nowhere to be found here. So we can skip all of this. We're not going to use any of that. Okay, then we can focus on this part, the first quadrant. You can see that both graphs are positive. They have y values that are positive in the first quadrant. Okay, so let's just find out now for which x values this would be. So these are the graphs where they have positive y values, but let's see which x values would this be for. So looking at these two graphs over here, this one has positive y values. If you map it down to the x-axis, look where it points, just after 1. Also map that down again to the x-axis. It's also just past 1. It's moving on the positive side, on the right-hand side of 1. And you can see it's doing the same thing for the straight line graph. These are also coordinates for the straight line graph. If we map it down, you can see that these are values that are greater than 1. They're x values that are greater than 1. So we always have to check. We have to answer them in terms of x. So we're checking for which x values these parts of the graphs belong to. And so this would be where x is greater than 1. So that is one of our solutions. This is where x is greater than 1. Okay, so we found the places where they were both positive. We found that. Now let's focus on the places where these two graphs are both negative. So remember, them being both negative, just we're referring to their y values. So we're only going to look at negative y values, meaning we're only going to look at this part of the y-axis with negative y values. So we're focusing this time on the third and the fourth quadrant. Okay, so we're looking for places where the both graphs exist. First of all, if we check here, we cannot even take this. Unfortunately, f prime of x is the only one here. It doesn't have g of x that has negative y values. If you look at this one and you see the x value that it belongs to, g of x values and y values unfortunately are positive, so we cannot even use any of this part. But if we keep going and we keep going, we need to see where do they both exist at the same time. So if we keep going, you see, unfortunately, this one is negative here, but that one is positive, so still not working. Still not working all the way here. Even here, it has a negative y value, but that one, its y value is 0. Okay. As we keep going over here, this small gap in here, you see now that we have the graph of f prime of x, the straight line and the hyperbola are existing here, meaning they both have negative y values here. So we just have to see now for which x values does this belong to. So where they both have negative y values, so I'm just going to mark the places where they both have negative y values, and that would be all the way here, this here, and here at the same time basically. So you see, all for these, they all have negative y values. So for which x values does this belong to? This will belong for these x values. So we're looking at like, we're taking this point over here and we're mapping it to the x-axis, mapping that to the x-axis. We're also doing the same for the blue graph, mapping it to the x-axis. And now you can see that this is happening between these two x values, where x is greater than 0 but smaller than 1. Okay, so for that one, that is where x is greater than 0 but smaller than 1. Now, I don't know, you may be thinking, why did I not say that x is equal to 0 in this case? Because if you look at the f prime of x, it has a negative value where x is equal to 0. But remember, we need to look at it, we need to account for this for both graphs. They must both have negative y values. And in this case, unfortunately, this graph of g, it doesn't have a negative y value. It has a y value of 0 itself. So we cannot consider that. So we have to say it starts where x is greater than 0, not equal to 0, but smaller than 1. Okay, so that is how to solve that one. So our answer is just basically x needs to be greater than 1, or x needs to be greater than 0 but less than 1. Now, funny enough, if you look at these values on the number line, we can actually write it as one simple answer. Because if you look at these, we have 0 and we have 1, and we're basically saying that x is greater than 1. So if we have 1 here, x is going towards those values. But here, we're saying that x is greater than 0 but smaller than 1. So if you look at this, it's really that x is greater than 0 because it includes all these values except for 1. X is just not equal to 1, but it is greater than 1. It's also less than 1. So you could have also written this as x is just greater than 0, but x is not equal to 1. But I'm sure if you left it like this, it would also be fine. Okay, and now the last question in this question 4 is, for which values of k will the equation of g of x equal to x plus k have two real roots of opposite signs? Okay, so this question is for 1 mark, so I don't think you need any delta or anything like that because it's 1 mark. So it's probably a graph interpretation thing. You have to look at the graph and actually see how this works. Let's focus first of all on the equations that they are referring to. They want us to find for which values of k will this g of x be equal to x plus k. Okay, so will this g of x be equal to x plus k? Let's separate first of all these two equations. We have the equation of g of x, which we know is that hyperbola, which has 2 over x minus 1 plus 2. Then we have another equation here, and that equation is x plus k. So if you look at that equation, it's really just y is equal to x plus k. That's that equation. This one is our g of x. So we have these two graphs, as you can see, this one is a straight line graph. It has the y is equal to x, then plus k, because this could move up or down. We need to find out which direction it needs to move first of all. But all in all, we have this y is equal to x. Now, that graph is this line. It's basically this perfectly diagonal line. If you have a Cartesian plane, for example, and you have, let's say, -2, -1, 0, 1, and 2, and you also have the same thing on the y-axis, then this is how this line is going to look. If your x value is, so I'm focusing on the y is equal to x part. So if we have an x value of -2, your y value will also be -2, because y is equal to x. If you have an x value of -1, you have a y value of -1. X value of 0, y value of 0. X value of 1, y value of 1. X value of 2, y value of 2. That's what I mean by it's that perfectly diagonal line. Okay, so this is just for you to know what that line looks like. So what they're doing with the graph of G and this line is that they're equating them, and they want to find out for which values of K will it have two roots of opposite signs. So first of all, let's look at this graph. Let's draw this graph. Since we already know we have the graph of g of x, let's draw this graph y is equal to x plus k, because it hasn't been moved yet. So the y is equal to x line, I'm just going to draw that as a diagonal line that will of course pass the origin 0 and 0, because when x is equal to 0, y is equal to 0 as well. So that is this line. So at first, when we're looking at this line, we can see that it has a y-intercept of 0 and an x-intercept of 0, of course. So that's that y is equal to x. Then I'm just going to include the plus k, because then we still have to think about how to move this graph. Let me change the color to red instead. Okay, so looking at this line, the question, remember, they want for which values of k will it have two roots of opposite signs. Okay, so I know that we know roots as x-intercept, and this is what I kind of do not like about this question. This question has actually shown up before. I think it showed up in a November 2015 paper, and they still use the words roots. And I know everybody knows that roots we only refer roots to x-intercept. But what it seems like they mean is we're looking at this graph, right? And we're looking for the places where the graph intersects with the graph of G. So we're going to look at the graph of G and this graph of y is equal to x plus k. And the roots that they're referring to, the roots of opposite signs, are, remember that they equated these two graphs. So we're looking for the points of intersection, but we're specifically looking for the x values of the points of intersection. And we want the x values of the points of intersection to have opposite signs. So we have to think about how should we move this graph. So I'm going to copy this graph and let's think about moving it down or up and see how we're going to move it in a way that it's going to intersect the graph twice as usual, but then it's going to intersect the graph in a way that the first point of intersection will have a negative x value and the second one will have a positive x value. Okay, so this is the graph copied. So I'm just trying to figure out how do we move it. Let's think about this. It was here originally, right? And when it's here originally, the intercepts or the x values of the point of intersection. Here we have, first of all, a point of intersection at 0 and 0. So this is neither positive nor negative. The second point of intersection that we have is over here. And that one has a positive x value. But we want the 2 points of intersection to have x values of opposite signs. That's the roots of opposite signs. That's what we're looking for. So let's think about moving it down. If you move this graph, anything just below what it was originally. So here, this is where k is equal to 0 at this line, because you can see the y-intercept is just 0. If you move it down, meaning we're making k smaller than 0, see what happens here. So if I move it down, look at where it intersects. It intersects over here and over here. Now the problem with this, and the reason I cannot accept this, is because at this point of intersection, let's look at the x value of this point of intersection. It's over here. It's a positive x value. And this one, its point of intersection, is also a positive x value. We don't want that. We want two x values that are of opposite signs. So if you move it down, it keeps on doing that. Positive x value of the point of intersection, another positive x value. So you see clearly moving it down does not work. We need to move it up instead. So when it is here at the point where k is equal to 0, we're going to just make k more than 0. Just make k greater than 0. So move it up instead. So if we move this graph up, look at where it intersects now. It intersects here and here. Over here, this point of intersection has an negative x value. And over here, the point of intersection has a positive x value. So you can see now these two have opposite signs. The points of intersection or their roots have opposite signs. So we just have to make k greater than 0. And then that's what would work for that. Okay, so for that last question, k just needs to be greater than 0. So I'm just saying that, therefore, in this one, k needs to be greater than 0. Okay, and that concludes it for question 4. And now we're on question 5. Question 5 says, the graph of h of x is equal to a to the power of x, where a is greater than 0, is sketched below. And then we have this point P. It's a point on H. The first question is to write down the coordinates of Q. Okay, I see that they didn't really tell you what Q is, but it seems like Q is the y-intercept. So let's go ahead and find the coordinates of Q, which is the y-intercept. In order to find the y-intercept, always make x equal to 0. So we're just going to do that. Make x equal to 0. So the equation of this graph, h of x, is just a to the power of x. So we're taking h of x being equal to a to the power of x, and we're just going to make x equal to 0. So this is h of 0 is equal to a to the power of 0. So h of 0 is equal to anything to the power of 0 gives you 1. And so that therefore means that q is just 0, that's the x value, and 1 is the y value. And then 5.2 says determine the value of a. Okay, so we know that h of x is equal to a to the power of x. And let's see on the graph, they gave us this point, -1.5. So that's our x value and our y value. So we're going to just substitute that into the graph. The y value is 1/2, and then the x value is, so a to the power of -1. That was the x value. So let's go ahead and just solve for a. Since we just have a to the power of -1, because this is a letter, we cannot make the bases the same. So we can focus on the exponents being the same. So since we have a -1 here, how do we rewrite this in a way that it's going to have an exponent of -1? So if you want to write a fraction as a whole number, just to make it look like a whole number, it won't be a whole number. You can write it like this. If it's 1/2, we're going to go ahead and just take the 2 to the numerator. But the consequence of that is that its exponent is going to be negative. The 2's exponent already here is just a +1. When you take it to the numerator, the exponent is now -1. Remember, it's still like a fraction, so it's 2/1. But if you say anything divided by 1, it just stays the same. That's how we have 2 to the power of -1 is equal to a to the power of -1. And now that the exponents are the same, we can equate the bases. So therefore it means that a is equal to 2. Okay, moving on to the next question. So we have to write down the equation of a to the power of -1. So that's the inverse in the form of y is equal to. So the original equation was y is equal to a to the power of x, but we know what a is now. So that is 2 to the power of x. So we just have to write the inverse in the form of y is equal to. To write the inverse, first of all, you swap x and y. So in place of y, I'm going to now say x is equal to, and then 2 to the power of x instead turns into y. And then now we just have to make y the subject after swapping x and y. So to make y the subject, we're going to have to use log because y is an exponent here. To make an exponent a subject, we're just saying y is equal to, and we're saying it's log of the base. The base is the one that's carrying the exponent, so it's our 2. And then we have x. Okay, so there we have written the inverse in the form of y is equal to. Then 5.4, we have sketched the graph of h of -1 in your answer book, clearly showing all intercepts with the axis. Okay, it's not like I'm using the calculator. I'm just going to make that smaller. Now, when sketching this graph is actually very easy to sketch. And I think many a time students overthink this. You already have things that you need here. You have 2 points. Focus on only those 2 points. You have P and you have the point Q, which is 0 and 1. We're only going to use those 2 points. So since we are sketching the inverse of H, just remember that the inverse of H is just going to have all the coordinates swapped. So instead of having this P, right, the image of P on the inverse is not going to say -1.5, it's going to say 1/2 and -1. And then this y-intercept is not going to be 0 and 1. It's instead going to be an x-intercept, and it's just going to say 1 and 0. Then you just have to know the shape of the graph and how it's going to look. So let me put down the Cartesian plane so we can look at that and only focus on these 2 points. Okay, so here's my Cartesian plane, and let me just focus on the numbers that I should have here. Remember, I'm not really using any other extra numbers. I'm only using things that I have on here. So if I see the number -1 and 1/2, I'm going to try and make sure I have that. I also have 0 and 1, so I'm also going to just make sure I have that on both axes just to be safe. Okay, so here is the Cartesian plane. And so now I'm just going to focus on the points that I have on the original graph. So since the original graph has the point -1 and 1/2, I'm going to have 1/2 and -1 instead. And I'm going to call that the image of P. So just P prime. So at 1/2 and -1, that's where we have P prime being 1/2 and -1. And then we have the Q. The Q was 0 and 1. So instead, we're going to have 1 and 0. And that's going to be over here. So that is our Q. I'm just going to call that Q prime. And it is now 1 and 0, which is an x-intercept. Okay, now that you have your points down, you have to just look at the way your graph looks. Looking at the original graph, look at what your original graph is doing. So we're looking at the x-axis, and you can see that this graph is coming from the y value of 0. It was closer and closer to here, and then it starts to increase as we move towards the positive parts of the x-axis. So this is the positive parts of the x-axis and the negative parts. So you see what it's doing here. It starts to increase, meaning the y values are getting higher. Okay, so it's increasing like that. What it's going to do on the inverse, it will just swap. It's not going to do the opposite, it just swaps. So your graph is just going to do what it was doing on the negative part of the x-axis. It's going to do that instead on the negative part of the y-axis. So your graph was closer to the x-axis at this point, on the negative part of the x-axis. So on the negative part of your y-axis, your graph is going to be closer to this point. Then as you can see, it starts to increase as it moves towards the positive part of the x-axis. The same way this graph will start to increase as it moves towards the positive part of the y-axis. So it's basically going to do this. It will start increasing like that. See? So it's kind of like tilting your head this way and then looking at it. And you're seeing that from here on the negative part of the y-axis, then you see what it's doing. It's increasing. And so that's what our graph is going to also do. So we can go ahead and look at it here. As you can see, you have a point here and a point here. The graph is just going to do this. On this part, it's going to be coming from here, and then it's going to start increasing and curve like that. So not the perfect graph, but that's basically what it's doing. So it's doing the same thing as what it was doing over here. Also, just remember that the original graph had, as you can see, that we just have a to the power of x. We don't have a q. Since we don't have q, it means that q is actually 0, meaning your horizontal asymptote is at 0, okay, on the x-axis. So it means that if your horizontal asymptote was here on the x-axis, then the inverse is going to have a vertical asymptote instead. So this one, the asymptote would have just been y is equal to 0, but the inverse is going to have an asymptote of x is equal to 0. And that's why your graph over here is just going to be moving closer and closer to the y-axis. Okay, so it's coming from a very close place to the y-axis, and then it starts to increase like that. Okay, so that's 5.4. Moving on to 5.5. And then 5.5 says, write down the domain of the inverse of h. Okay, so when we're speaking about domain and range, let's just look at what happens. If you have an original graph for O and an inverse, the domain of your original becomes the range of your inverse. And the range of your original becomes the domain of your inverse. So it basically just swaps. So if you want to find out what the domain of the inverse is, you have to know what the range of the original was. Let's look at the original graph. We know that the original graph, the equation was that h of x is equal to 2 to the power of x. And remember, the value of q is 0. So to find out what the range of this graph is, remember the range is all the possible y values. If the graph lies above the asymptote like it does right now, as you can see, then it means that the range, the y values, are just going to be greater than your value of q, whatever your horizontal asymptote was. So we already know what q is here. We know q is 0. So it means that the range of this graph of h is y is greater than 0. Okay, so now that we know that range, if we know that this range is y is greater than 0, they're asking for the domain. So it means that this is the domain of this. But we cannot write it as y is greater than 0 because it's a domain. It's speaking about all the possible x values. So it means that the domain is going to be x is greater than 0. So see, it's still the same thing. We're just referring to x values now, not y values, because it's the domain. And then moving on to 5.6, the second last question in question 5. So 5.6 says, hence or otherwise determine the value or values of x for which log base 2 of x is greater than 0. So this is our equation of the inverse of h. So we have to find out where is this greater than 0. It's for 1 mark, so it's something that you have to do on the graph. So let's look at the inverse and look for places where it is greater than 1. Remember, where they say it's greater than 1, they're referring here to the y value. Just like you would have said, h of negative 1 of x is equal to log have a base 2 and x. You can see that this, okay, is referring to this, which is a y value. We're speaking about all the y values. So which places does this graph have y values that are greater than 1? So we have to look at the graph for that. So looking at this graph that we have, where are the y values greater than 1? So we have a y value of 1 over here. And so let's see where that maps to this graph. Okay, so right now I cannot see the graph. I'll just have to extend it. Okay, so this is not the best graph, but it looks something like this. And so I'm trying to first of all find out where are all the places where the y values would be greater than 1. Okay, so over here, this is where the y value will be equal to 1. And we have to find out for which x value this would belong to. And I'm just going to extend the x-axis. So over here, we have some sort of point here, coordinate here, that has a y value of 1. So let's find out what that x value would be. So to find out what x value this would be, you would need your equation of this graph of h of negative 1, the inverse of this, so this graph. And the equation of that graph is h negative 1 of x is equal to log the base of 2, and we have x. So if this is the equation of that graph, let's just find out where does it have a y value of 1. So we can just find out where exactly is this starting. So to find the y value of 1, we're going to substitute in place of y, we're going to put in 1 there. So 1 is equal to, and we have log base 2, and we have x. So here we have to put it in exponential form to solve for x. So in exponential form, we know that the base of what we have is going to be 2. So we're going to have 2 to the power of, now your exponent is going to be what this was equal to. It was equal to 1 because it always makes the exponent the subject. So to the power of 1, and that is now equal to your x. That's how to solve for x. So it's equal to what's inside the bracket. That will be your answer in exponential form. And you can use this to remember this. So now we know that that x value is equal to 2. Where the y value is 1, we have an x value of 2. So all this is asking is for the places where this log base 2 of x is greater than 1. Okay, where does it have y values greater than 1? So let's look on the graph. On the graph, if this is your y value of 1, then below this, all these parts of the graph have y values that are less than 1. We need to focus on the ones that have y values greater than 1. And that will be all these parts of the graph, because this graph is going to keep increasing. So these parts of the graph have y values greater than 1. And so if we map this down to the x-axis, we just have to map it down like this. We map it down, down, and we see now that these are values that are greater than 2. Okay, so not equal to 2, because they want the y values to be greater than 1, not equal to 1. At 2, the y value is equal to 1. So where the y values are greater is just where x is greater than 2. So I'd actually put all of this calculation in that answer. So this is therefore where x is greater than 2. Okay, so 5.7, the last question says, if g of x is equal to 100 multiplied by 3 to the power of x, calculate the value of x for which h of x will be equal to g of x. So remember that h of x was that 2 to the power of x. So we have to equate this and just solve for x. So we're saying that h of x, the 2 to the power of x, is now equal to this g of x, which is 100 multiplied by 3 to the power of x. Okay, so when solving for this equation, please notice that 2 to the power of x and 3 to the power of x, they have the same exponent. So let's try to put them together so that we can write them over the same exponent. So what we can do is, to get the 3 to be on the 2 side, we basically have to get rid of this 3 to the power of x on this side. And the only way to do that is to divide both sides by 3 to the power of x. Then it will be gone. Then we see that these two would cancel. They're gone now. And now you just have 100 on this side. So here you have 2 to the power of x and 3 to the power of x. You can write it as 2 over 3 all raised to the power of x, since they're both raised to an exponent of x. That is equal to 100. And now we just have to solve for x. As you can see, this is a fraction. This is 100. You can't really make the bases the same, so you just have to use log to solve for this. So log makes the exponent the subject. So we're saying that x is now equal to log, our base is still this because it's the base carrying this exponent. So base 2 over 3, and then here we have 100. So we're just going to substitute this and see what we get. And when we substitute this, we see that we get x being equal to, and we can just round off the 2 decimal places, so negative 11.36. Okay, so that is our answer. Okay, so that's it for question 5. Question 6 says the graph of f of x is equal to negative square root 27x for x being greater or equal to 0 is sketched below. The point P, which is 3 and negative 9, lies on the graph of f. And the first thing we have to do is use the graph to determine the values of x for which f of x would be greater or equal to negative 9. So remember, they are referring to a y value of negative 9. So let's just mark the places where this graph, or where the y values of the graph will be greater or equal to negative 9. So if this is negative 9 over here, negative 9 is here. The places that are greater than negative 9 would be above here. So we're taking all the parts of the graph that are above this line. But because it said greater or equal to, we'll also take that point as well and every other x value above it. So let's see what the x values for this are. First of all, where y, or where the f of x, the y value, is equal to -9, that is where x is equal to 3. Like they told us already, it's a 0.3 and -9. Then the places on the graph where this is greater than -9 would be here. So let's just group this and line this up to the x-axis. It'll be all these highlighted spots on the graph. And as you can see, these will be places that are in between 0 and 3. But also notice that at the point 0, we have 0 and 0, okay? And 0, the y value of 0, is also a number that would be greater than -9. So your answer for this would be, it's between 0 and 3. X is going to be greater or equal to 0. So it's not just greater than 0, because 0 is also an included point. At this point 0, the y value is 0. 0 as a y value is also greater than -9. So we have to include that as well. So it is x is greater or equal to 0, but less than or equal to 3. And the reason why it's equal to 3 here again is because they specifically asked for places that are greater or equal to -9. And we know that at the x value of 3, the y value is equal to -9. Okay, so that is the answer for that first one. And then question 2 says, write down the equation of the inverse of f in the form of y is equal to, and then you need to indicate all restrictions. So they're referring to this restriction. They restricted the domain of the original graph, so you also have to show your restriction as well. Okay, so just finding the equation of this. First of all, we can write it as y is equal to the original one, -27x. And then to find the inverse equation, first of all, just swap x and y. So I'm going to say x instead is equal to -27, and in place of x, I'm going to put y. Okay, now we just have to make y the subject. So if y has to be the subject, we need to get rid of, first of all, the square root. So to get rid of the square root, we're going to square both sides. So if I square that and I square that, this is what we get. We get that x squared is equal to, now the negative is going to fall away because a negative times negative is positive, and then the square root also falls away because it's the inverse. So we have 27y. And then to make y the subject, we'll just divide both hand sides by 27, and so therefore y in that form is equal to x squared over 27. But now we also have to put a restriction for this inverse. Now to put the restriction for the inverse, first look at the restriction for the original. The original has a domain of this. This is the domain. Remember, with the original and the inverse, the original graph, if it has a domain, this domain will now become the inverse's graph's range. And then the range of the original graph will become the domain of the inverse. So if you look at this graph as our original graph, if its domain was x is greater or equal to 0, so that was the domain of this one, x is greater or equal to 0. We have to find out what is the range of this original graph so that we will know what the domain of the original graph is. That's the restriction you're putting. You only put a restriction on the domain, and that will have an effect on the range. So we need to put a restriction here. We need to find out what the domain of the inverse is. To find out the domain of the inverse, we're just going to find the range of the original. Okay, so with this one, it's quite simple because they already just gave you the graph. They already sketched it. So we can look at this graph and see what are all the possible y values of the graph. If we know that x can only be greater or equal to 0, so meaning you only have these x values, greater or equal to 0, look at the y values that you have. Your y values, notice that you do not have any positive y values. There's no graph up here. Your y values are, it's either equal to 0 because we have a y value of 0, or it is less than 0. So it means that here, our range of this, the range is y is either less than or equal to 0. And so if this is the range of the original graph, then the domain of the inverse would be x is less than or equal to 0. Okay, because that's what it becomes. The range of the original becomes the domain of the inverse. But I cannot call that y because it's still domain, so it's still speaking about the x values. So that would be the answer for that. So it's this, and then you need to say where, or put a semicolon and say this is where x is smaller or equal to 0. That's the domain of the inverse. So question 6.3 says, sketch the graph of the inverse of f in your answer book. Indicate all intercepts with the axis and the coordinates of one other point on your sketch. Okay, so you have to have intercepts, so x and y intercept, but in this case, it's definitely just going to be one intercept. It's just going to be that 0 and 0 because that is both the x and the y intercept. And then you also have to include one other point, so possibly the point that they already gave us here. Okay, so you don't have to now start sketching it using other points. You can just use what we have here. You know that this is the original. The inverse of it will just have all the coordinates swap. So if we had 0 and 0, the inverse will also just have 0 and 0 because they are just swapping. And then here, if our coordinate for P was 3 and -9, our coordinate for P on the inverse would be -9 and 3. So let's go ahead and just put that down first. So we have our Cartesian plane, and we know first of all, we have the coordinates 0 and 0, and then we have -9 and 3. So 0 and 0 in the center, -9 and 3 will be somewhere here. Let me just extend this. So -9 would be here. So 9 places, 9 blocks, I'm just moving. -9 and then 3 up. So we have that. -9 and 3. I'm just going to call it the image of P. So P prime, -9 and 3. Okay, so we have that point now. We have the center and we also have that point. Now just to sketch the graph, monitor the way your original graph looks. So it looks like this. If you tilt your head to the right, you will see that this original graph, if it was a full parabola, it would be concave up. So kind of like imagine this like that. It will be concave up, just tilting your head to the right. So it means your inverse will also be concave up. So if it's concave up, and we can see that it is concave up facing the positive part of the x-axis, the inverse will be concave up facing the positive part of the y-axis. Okay. And we know our coordinates were over here, so it's going to be concave up facing like this. Okay, so that's how to look at it. That was just to let you see that it was like from an original parabola. It was just restricted. So we can go ahead and just draw that over there. It's going to come from the center and it's going to just curve out like that. Something like that. Let me just make that look better. Okay, so something like that, and basically just shoots out. So that's what your parabola is going to look like, the inverse. So you can also just label it f -1. Okay, so that's it for 6.3. You can, if you like, call the 0 and 0, but as long as they can see it is touching the origin, they will know that is the center. Okay, then moving on to 6.4, the last question in question 6. Okay, so 6.4 says, describe the transformation from f to g if g of x is equal to the square root of 27x, where x is greater or equal to 0. So g of x looks like this, square root of 27x. But f of x was negative square root 27x. So if you look at these two, you see that this one had a negative and that one had a positive. So clearly this was multiplied by -1 in order to get that one. So when you're multiplying this by -1, it's like multiplying the y value because f of x is equal to this, right? So you're taking all the y values and you're multiplying it by -1, meaning you have caused all the y values to change. So it means that the transformation that happened here was a reflection. And since all the y values changed, it means that it was reflected in the x-axis. So this is a reflection in the x-axis. So it just basically means that f is reflected in the x-axis to form g. And that's it for question 6, and that's it for functions. So moving on to question 7, we have financial maths.